Let's build one of the most classic and satisfying shader effects out there, the infinite flying tunnel. You've probably seen these hypnotic animations before and assume they must be incredibly complex, right? Well, the math is surprisingly simple and ton of fun to customize. So fire up ShaderToy or any other tool you want, and let's bring this thing to life. Hey, I'm Pavel, I'm a computer scientist with a PhD in the field, engineering manager and a software developer with over 15 years of experience. On my channel, we talk about interesting computer science topics. So, how do you create the 3D looking tunnel without any 3D models? The secret is in how a pixel shader, fragment shader thinks. It doesn't know about objects. It only knows one thing. For every single pixel, in this case every single pixel on the screen, it must decide what color it should be. Our job is to give it the right math to create our illusion. We are going to calculate each pixel's color based on its position. First, we need a good coordinate system. A pixel's coordinate, frag coord, might be something like 860. That is not very useful in this case. We normalize it, so the center of the screen is 0, 0, and the edges are around -1 and 1. We'll call this coordinate UV. Last episode, we used different range for UV, but it really doesn't matter. Just be aware of what is happening. Next, we calculate the distance from the center to our pixel's UV coordinate. This is just the length of the UV vector, which we call R for radius. Now, for the magic trick, we create a depth variable, z, by taking the inverse of the radius. Think about it. A pixel close to the center has a tiny r, which means its z will be huge. A pixel far from the center has a large r, so its z will be small. This simple formula perfectly fakes perspective. After calculating our depth, z, we get to line float color value is equal to modulo z1. The modulo function gives us the remainder of a division. By taking modulo z1, we get a value that smoothly repeats from 0 to 1 over and over again as z increases. This creates the repeating band of our tunnel, a smooth gradient from black to white, which then snaps back to black and starts over. Next in line, the color equal to vec3 color value, a color needs 3 components, red, green, and blue. By creating a vec3 and giving it the same value for all 3 components, we get a shade of gray. A vector 0 is pure black, 1 is pure white, and 0.5 is medium gray. So this line takes our repeating black to white gradient and makes it an actual color. Then we add a finishing touch and update the color for power 1 minus R, 10, which creates that bright light at the end of the tunnel. Remember R? That's our radius, 0 at the center and increasing outwards. So 1 minus r is a value that's 1 at the very center and fades to 0 at the edges. The power function raises this to the 10th power, which makes the fall-off incredibly sharp and intense. The result is a small, bright, white hot glow right at the center. We simply add this on top of our ring colors. And finally, we have a frag color is equal to vector 4 color 1, which assign our final calculated color to the output variable frag color. The 4 component 1 is the alpha channel, making the pixel fully opaque. And that's it. The foundation is now set. A static tunnel is cool, but a flying tunnel is way cooler. To add a motion, we need a value that changes over time. ShaderToy gives us a perfect built-in variable for this, which is itime. This is just a clock that's always running. To create forward motion, we simply add time to our depth calculation. Instead of modulo z1, we'll do something like modulo z plus itime for 1. This makes the pattern slide over our virtual tunnel shape, creating a powerful illusion of flying forward. But flying in a perfectly straight line is a bit boring. Let's make the camera move. We can do this by offsetting our UV coordinates before we calculate the radius. By using sine and cosine, we can make the camera move in a smooth circular path. Let's also upgrade our coloring. We can calculate the pixel's angle using a tan for y and x. By combining this angle with our depth z, we can create beautiful swirling spiral patterns. Let's take a closer look at that last section, the glow, to see how we add that extra layer of atmosphere. First line of our glow effect is float, is center glow, power 1 / r times 10 plus 1 for 5, which defines the shape and the intensity. The expression is another way to create a fall-off effect. When r is 0 at the center, we get 1/1, which is 1. As r gets bigger, the denominator increases and the value shrinks towards 0. We then use power 5 to make this fall-off much sharper, creating a tight, bright hotspot. Center glow then is a number that represents the brightness of our glow at any given point. Next, we define the glow's color using a mix, where the mix blends between two values. Here we are blending between two colors, which are white hot color and orange. The third argument, r times 2, is the mixing factor. At the very center, r equals 0, we get the white hot color. As you move away from the center, r increases and the color smoothly transitions to orange. This creates a much more realistic glow than a single solid color. Finally, we combine them together as a glow color times center glow times 2. Here we take our beautiful color gradient and multiply it by our brightness mask, which is center glow. This ensures the color only appears in that bright central spot. We then multiply it by 2 just to boost the intensity and add it right on top of our existing spiral colors. And with that, our tunnel now has a beautiful atmospheric glow at the end, making it feel much more interesting. Alright, we have a great animated tunnel, but now it's a time to add the professional polish. We are going to add 4 key upgrades: a rotation, a more dynamic speed, a realistic atmospheric fog, and finally clean, solid, anti-aliased walls. First, let's make the motion more interesting. We'll add a slow, continuous rotation to the entire coordinate system. We do this with a 2D rotation matrix, right after we offset the camera. You already know 2D rotation matrix. Next, instead of a constant forward speed, we'll create a varying speed using a sine wave. This will make our flight gently accelerate and decelerate, giving it more organic feel. Let's look at the line of code. Varying speed is equal to 1 plus sine I time 0.5 times 0.5. We can visualize how this builds the effect step by step. Sine I times 0.5. This creates a basic sine wave that oscillates between -1 and 1 over time. The 0.5 inside the function just slows down the frequency of the wave. Second step, times 0.5, this shrinks the wave's amplitude, so it now oscillates between -0.5 and 0.5. Finally, we add 1, which shifts the entire wave up. Instead of oscillating around 0, our speed now smoothly oscillates between 0.5, which is 1 minus 0.5, and 1.5, which is 1 plus 0.5. So the varying speed variable smoothly cycles between a half speed and 1.5 speed, giving our tunnel that captivating rhythmic pulse. Now the biggest visual upgrade. First, we'll add fog to create a sense of depth. We'll define a fog color and then mix it with our tunnel color based on the distance z. An exponential function, minus z times constant, is perfect for realistic fall-off. Notice these artifacts in our render. Look closely at the end of the tunnel. You can see the rings shimmering, breaking apart and creating these distracting wavy patterns. This is a classic computer graphics problem called aliasing, and in this case moire patterns. These artifacts happen when we try to draw details that are smaller than a single pixel on your screen. The graphics card gets confused, not knowing whether a pixel should be black or white, or whatever, which results in that ugly flickering mess. It's like trying to draw a razor-thin line with a thick permanent marker. The solution is in smart blur that only affects the problem areas. We can achieve this with one powerful line of code. This line uses two superhero functions to eliminate aliasing. First is fWidth, which is the detector. This is a function which is a key to detect how fast our pattern is changing at any given pixel. In the distance, where the rings are squished together, fWidth reports a large value, telling us, warning, high frequency detail ahead. Up close, it reports a small value. Smooth step is the fixer of the problem. This function takes the information from fWidth and creates a perfectly soft edge for our hard lines. Think of it as automatically switching from a sharp pen to fine airbrush right at the edge of a shape. By combining these, we get a result that is both sharp and clean. The shimmering mess at the end of the tunnel is replaced by stable, solid rings that fade smoothly into the distance, while the rings close to the camera remains perfectly crisp, which is the important thing. Let's put it all together. We will now calculate the base tunnel color, mix it with the fog color, and then multiply the result by our wall mask. And that's how you do it. We took a basic formula and layered on simple ideas to create a dynamic polished animation. It just goes to show that even the most complex effects are built from simple, clever building blocks. Use this code and play around. Change the colors, tweak the speed, mess with the fog or geometric functions. It's the best way to learn. That would be all for today. Thanks for watching. If you like what you saw and want to see more in the future, hit the subscribe button. See you next time.